Okay. All right. So your homework assignment incorporates ggplot. If you want to like recode your thing so it doesn't use ggplot, that's fine. I'll allow it. Okay. But if you want to use ggplot, but you don't know how, there's some good things out there, right? Well, first of all, you can just type in ggplot into Google, and it's part of the ggplot universe. You can just click, your first thing, ggplot 2 as part of the tidyverse, and pretty much under all of the reference stuff, they have how to use each geometry. Okay, and there's a few things. I can also post up some notes. The other, I think, very useful thing is, and everybody who's a UCLA student should take advantage of this resource, is Safari Books Online. And the web address is, I don't know if you guys can see that, ProQuest.SafariBooksOnline. This is like really great, okay? So, you know what, I gotta fix my, something's wrong with my mapping here. There we go. Okay, so we have ProQuest.SafariBooksOnline.com. All right, and so this is free access to from the UCLA network. So while you are connected, while you're on campus and you go to ProQuest.SafariBooksOnline, you can go through the thing, library here. If you're at home and you go here, it's going to deny access. All right. So you have to use the VPN or something to get access. Okay. So if you're at home, you need to VPN into the thing. But basically, it gives you the entire library of O'Reilly books. Okay. And what you'll search for is the R Graphics Cookbook. I think this is linked in your syllabus, but the R Graphics Cookbook makes use of ggplot, and it's very good. I mean, the book is already 6 years old, but everything is still super great. You know, like in the computer world, once a book is over a few years old, it's like you got to throw it away. But this is still it still holds up because ggplot has since expanded and has done more, but its basic functionality has remained the same, right? It's kind of like picking up an old book on C. Like, a lot of those concepts still remain the same, even though, you know, C++ has greatly extended it, okay? So anyway, you know, you're like line graphs and how to, you know, adding points to a line graph and stuff like that. So, you know, all of these, it comes with little recipes on how to draw the thing that maybe you want to draw, okay? And then the other part is you look at the geometries, and you can do it. And so here I think we have geom segment, which is probably one of the tools that you'll be using, and then there's all sorts of examples. These are geom curves, but you know, it applies. Okay, and I'll also post my notes for ggplot. Unfortunately, in the summer session, we don't have time to devote a full lecture to ggplot, unfortunately. But it is kind of, you know, it's not like a thorough thing that you have to do in the homework. The homework focus is mostly on these numeric methods here. Okay. well, while we're talking about Safari Books Online, you know, there's other things. I know a lot of you guys are interested in Python, so there's all these great books. You can just type in Python data, and the top 2 hits are the Python Data Science Handbook and Python for Data Analysis, 2nd edition. These are both excellent, okay? Python Data Analysis is written by Wes McKinney. Wes McKinney is the inventor of the Pandas package for Python, okay? Which, you know, if you've done any work in Python and worked with data frames, you know, you have to import pandas. And so he wrote this. It's very, very good. These are, like, if you buy the print book, it's like $60 retail, probably $35 on Amazon, but it's free, legal and free here, right? I mean, of course, you can probably find illegal versions on the internet, but this is something that is free to UCLA, because, well, not free to UCLA. UCLA, part of your tuition money goes towards the library services at UCLA, right? And the UCLA library subscribes to these services. So in a sense, you are paying for it, but it's like hidden in your tuition costs. So take advantage of the resources that you're paying for. So anyway, Safari Books Online, an excellent resource. Okay. Any comments, issues, questions before we move on? We're all good. Okay. All right, so let's get started on today's stuff. So on Tuesday, we talked about floating point numbers in the computer. So that's how the computer sees numbers, okay? And so, you know, we're accustomed to real numbers where, you know, 1/3 times 3 is equal to 1. But, you know, in floating point numbers, some of these things don't quite work out, right? 0.2 plus 0.1 is not equal to 0.3 in floating point. And so these are things you have to watch out for. You know, your homework covers, you know, what are these smallest normalized and denormalized values. And it kind of gets at the idea of, you know, how small can the computer distinguish from one value to another? And that's known as your machine epsilon. And you want to stay kind of, make sure the calculations you're doing avoid that, right? And so for that reason, when you're dealing with really small probabilities, let's say, you know, what is the probability of this, like you flip a coin 100 times, okay, and, you know, what's the probability of getting an exact sequence of heads and tails, okay? That's going to be 0.5 to the 100, right? And so you're going to get this very small probability. And if you want to do operations and compare that to another thing, a lot of times, instead of dealing with the probability directly, we will deal with the log of the probability, because the log of a very small number just becomes a very negative number, right? So probabilities are always between 0 and 1. So the log of that will be between -infinity and 0, okay? And so it scales everything. So instead of having to deal with, you know, 10 to the minus 400 or something like that, which the computer is not able to represent 10 to the minus 400 in its system, right? It's not able to do that. We see that the smallest non-zero number, dot machine x min, double x min is the smallest number it can represent is 2.2 times 10 to the negative 308, okay? And this is going to be a very non-precise number because it's denormalized. So, you know, things like 10 to the negative 400 cannot be represented on the computer. It's gonna say that's 0, right? If we say 10 to the negative 400, it's gonna say that's the same as 0. But instead, we'll deal with logs, okay? And so what we can do is we can do log of 10 and multiply this by negative 400, right? So we can deal with that, and this will give us a value that we can work with, and we can compare. Is 10 to the negative 390. So the computer thinks that's 0, but obviously we can say which probability is bigger. I mean, this is silly, but we can just say negative 400 times log 10 and negative 390 times log 10. These are numbers that we can actually compare, whereas the computer is not able to compare 10 to the minus 400 versus 10 to the minus 300, because in both cases the computer sees those as 0, right? So these are some of the things that we have to do when working with computers and small values, because the computer only has a limited number of values that it can represent, right? Okay, so I'll just say side effects of floating point representation. Okay, so we are unable to store very small values close to 0. So i.e., or for example, e.g. 10 to the minus 400 becomes 0 in the computer. Okay, 10 to the minus 390 also becomes 0, right? So, if you have if you want to compare two probabilities, A is equal to 10 to the minus 400, B is equal to 10 to the minus 390, okay? You cannot do A greater than B, okay? Because the computer sees both as 0. Okay, so instead, we will find A using find the log of A and the log of B. And obviously you can't just do log of 10 to the minus 400 and log of 10 to the minus 390. You have to do, you have to compute this some other way, right? So this will be minus 400 times log of 10 and minus 390 times log of 10. Okay, and now we can make a comparison. Okay, and this will be false. All right. So these are just things to think about in the future. Okay, and when you're dealing with regular numbers, maybe we don't worry about it, but on the computer we can't represent that. Okay, I'm going to get into this topic of root finding, and it's all part of, I guess, under the umbrella of numeric methods. So numeric methods, these are like tools that the computer can execute. Okay, so this is kind of like a series of operations to give to the computer to to get an answer for kind of a mathematical problem. Okay. So, for example, eventually we will want to do optimization, right? So optimization is just finding the minimum or maximum of a function. Okay, and we'll just deal with local mins and local maxes. Okay, so optimization is finding the minimum or maximum of a function, and in kind of traditional math, what we do is we calculate a derivative. D dx of your function. Okay, and so we'll get f prime of x. We set f prime of x equal to 0 and solve for x. Okay, and these are critical points. Okay, and then the critical points correspond to local min, max, or saddle point, right? Okay. Computationally, all of these things, like the computer doesn't know how to do any of this stuff. So computers don't know math, don't know how to do math. They can only compute. Okay, so if we want to do optimization, we'll look at a series of methods that are based on root finding methods, okay? So we'll have a few methods based on root finding, okay? Okay, and this is basically having the computer solve some function equal to 0, okay, which is basically have the computer solve, g of x equal to 0, okay? And basically, to apply to optimization, it requires us to take the derivative, so we have function f of x to optimize. Okay. We find f prime of x, and we'll call that g of x, and we use the computational method for solving g of x equal to 0. All right. So that's one thing we can do. Okay, and then we'll explore a few other methods. We'll see how far we get today. But yeah, so we'll start off with just some root finding methods. Okay, which to us seems very like simple, right? Like you just have a function, you set it equal to 0, you move some terms around, do some algebra, you solve for x, and figure that out. For the computer, it's a lot harder, okay? It doesn't understand these rules of moving things around, and it just plugs in numbers and spits things out, okay? And so so we'll look at some root finding methods, okay? Okay, and this is all covered in the Spurs textbook, the scientific programming and with using R or something like that. Okay, root finding methods. These are getting the computer to solve g of x equals 0. Okay, so first up, we'll have a fixed point iteration. Okay, so a fixed point of a function, we'll call it h of x, is where h of x equals x. Okay, so you plug in a value and you'll get a fixed point if you plug in x and it gives x back. Okay, so for example, if h of x is equal to x squared, right? X equals 1 is a fixed point of h of x. And it's basically, so you've got this thing, right? X squared. And you've got y equals x. This right here is a fixed point. Okay. So what we do is if you want to solve for the fixed point of a function g of x, I mean not g of x, you want to solve for the root of g of x, you just kind of rewrite g of x in some form so that the fixed points of h of x will be the roots of g of x, okay? So to use the fixed point method, to find the root of g of x requires us to rewrite g of x in a form h of x so that the fixed points of h of x will be the roots of g of x. Okay, so finding a fixed point of h of x will give us the root of g of x, okay? I apologize if my letters F, G, and H don't match up with what the textbook uses. I hope you guys are okay with that. All right. Okay, so for example, let's say we have a function g of x equal to log of x minus e to the negative x. Okay, so g of x is equal to log of x minus e to the negative x. Okay, we want the roots of g of x. Okay, so we want to know where g of x equals 0. Okay, so what we can do is, there's a few things we can do. We can set g of x equal to 0, and so we have log of x log of x minus e to the negative x equals 0. And then, and we can do e to this and e to this, right? Or you know what, actually, let's not do that. Sorry. Let me just move some terms around here. We'll do log of x is equal to e to the negative x, right? And then if I do e to this and e to this, then I get x is equal to e raised to the e to the negative x, okay? And then I can say, okay, well, let h of x equal e to the negative x, okay? And then, and fixed points of h of x will correspond to roots of g of x. Is that okay? Because where this thing is true, okay, right? When we say h of x, fixed points of h of x is where h of x equals to x. This will work, right? All right, or there's other options, right? And there's many possibilities. Another option, okay, is we've got g of x equal to log of x minus e to the negative x equal to 0. All right, and I can say, let's subtract both sides from x. Okay, and so I get x minus the quantity log of x minus e to the negative x, okay, is equal to x minus 0, right? So this just becomes x. All right, and then I can just call this thing h of x, all right? And we'll just say, okay, again, solve for h of x equal to x, and this will correspond to roots of g of x, okay? And I'm sure you could think of other ways to just rewrite g of x into a form h of x so that the fixed points of h of x will correspond to the roots of g of x, okay? Is that all right? Okay, and then the algorithm itself is like the easiest thing ever, okay? The fixed point iteration algorithm. Okay, so you have, you just start at some arbitrary x, we'll call that x sub 0. And then all you do is okay, and then we assume you have figured out h of x, okay? And this is the algorithm. Okay, the next value, so this is x at time n plus 1 is equal to h, apply the function h to the current value of x sub n, okay? That's it. Just take your current value, x sub n, plug it into the function h, and what it gives back, that will be your next value of x sub n. And then you plug it back in, and you just keep going. So just keep applying. So take your value, plug it into the function. Plug into function, okay? What it returns will be your next value. And it seems ridiculous that such a stupid thing would work, but it does. It figures out fixed points as long as, and there's a tough tough criteria. So this will work as long as the derivative of h of x at the fixed point is less than 1 at the fixed point. All right, let me just kind of illustrate this. So okay, and then let me draw this line. So this represents the line y equals x, and then we'll have a function here. Okay, so this is the fixed point, right? And this is y equals x, and this is our function h of x. Okay, so you just plug in some arbitrary value x sub 0, and okay, so if I plug in x sub 0, this takes me to right here. Okay, so I ask, all right, what is, so this corresponds to the value right here. This value is h of x 0, right? Okay, and so h of x 0 corresponds to this location right here, yeah? So this is h of x 0. This becomes my x at time 1, okay? So we're going to use h of x 0. This becomes x at time 1, and I come up and I say, all right, what is h of x1? That comes right here, okay? And then I say, all right, what is this? It comes over here. And so this is h of x1, and we're going to use this as x2. Okay, and so this comes down to right here. This will be x2. This is our h of x at time 1. It becomes x2. And you can see that if I continue this, it's going to get closer and closer to the desired value. H of x2 becomes our third iteration, and we keep getting closer and closer and closer. Is that okay? And so this will give me the fixed point eventually. Right? So we just keep converging. All right. Questions?
What if the curve looks like this?
Yeah. So if the derivative is steeper than 1, then it will diverge. Yeah. So it requires you to. So when I was going and trying to figure out what a suitable thing would be. Oops, that was not it. Okay. I could have said, let's add this to x to both sides, but if I did that, then the derivative would be greater than 1. And so you know, it would not be suitable. So yeah, you could try out certain things and it might not converge. Okay. There is a question?
Is it okay to find the inverse function?
Yeah. I mean, if you want to do that. So yeah, if it goes up, you can figure out the inverse and stuff. So, but I mean, so that's one iteration. I mean, one example. It's just a very simple thing, right? And so probably your most familiar example of this is like the square root function. The fixed point of the square root function is 1, right? And maybe when you were a kid in elementary school, you typed in like a big number on your calculator, 1 billion, and then you hit the square root and it gave you a smaller number, and you hit the square root button again and it gave you a does the calculator on let me see if the calculator will do what I'm talking about, right? So let's say I type in like, this is the number I'm going to start out with, right? And if I take the square root, I get this. And then if I hit the square root button again, I get this. And if I hit the square root button, I get this. And what is this going to converge to eventually? It's going to converge to 1, which is the fixed point of the square root function. Okay? And similarly, if you just keep applying the same function to a certain value, it will reach a fixed point as long as that condition of the absolute value of the derivative at the fixed point is less than 1. Okay? And so, you know, we can keep hitting the square root, and it's going to just get closer to 1. Okay? Until we get to a point where the computer is no longer able to distinguish it from 1. Let's see how good my computer is. Okay, and then it says, all right, I give up. It's 1. Okay? But that's that. Okay? So that's fixed point iteration. I think it shows up in your homework, right? Let's see. So I wrote this, and okay, and I set up a data frame for the drawing the line segments. But basically, the iteration, the algorithm itself is take your current value, your newest value, you set it to your old value, you apply the function to the old value, and that's going to become your new value. Okay, and that's it for the actual iterations. This is just some jibber jabber about storing the values to keep track of. Okay, but this in of itself is it. Okay, take the latest value, we'll call it the old, apply the function to it, and that will be your new latest value, and then loop. And you just do that over and over and over again. Okay, so that's fixed point iteration. Okay, it's not too bad, right? Okay, let's see. Other root finding methods. Another root finding method. And this one you might have actually learned in like high school or something. And this is the Newton-Raphson method. Do you guys remember this? Newton's method? That should sound familiar to some of you. No? Okay. I'm not crazy for imagining that this is covered in high school, right? Who's Raphson?
Yeah.
Some other guy? I don't know. Okay, so let's say this is your function, okay? And this is how Newton-Raphson works, right? You start at arbitrary, oh, not arbitrary, we'll say start at x0, okay? This is x0, and then this is our root, right? So this is no longer fixed point. Fixed point, you're finding where the function is equal to x, and you had to like rework the function to do this. Okay, this time, here's our function. Our function is g of x, okay? And then this is our root. The root is where g of x equals to 0. Okay, this is the root. This is what we want. We're going to start at x0, right? And then, yeah, no, that's fine. Let me just move my x0 on this diagram. It's too close to the edge here. Okay, so let's say this right here is x0, and so I come to the line right here, okay? And this spot right here, this is going to be g of x0, right? So we find g of x0. And then we draw a tangent line from g of x0 to the x-axis. Okay. So let's see. The tangent line will be this color. And I don't know, does that look like a tangent line? Something like right here? Does that seem reasonable? Okay, so we'll say that is the tangent line. Maybe it's not, okay. But so you draw the tangent line, and then where the tangent line crosses, okay, where the tangent line crosses the x-axis, will be your next value. Okay, so this will be x at time 1. Okay, and then what do? We come along here, we go up, and we repeat. So we come up to right here, and then I draw a tangent line, something like that. And this becomes x at time 2. And then I draw a vertical line. I draw a tangent line. And so on and so forth, okay? So that's Newton-Raphson method, right? Does that look kind of familiar-ish, maybe? Okay. So how does this work, right? All right, how do we get the location x1? What? All right, so let's say so if we're currently at x at time n, how do we get the next value? Okay. Well, what we need to do is if we're gonna label these triangles, we got rise and we have run, right? Okay. And the slope is rise over run, right? So we can say x at time n plus 1 is going to equal x at time n. So if we're at x0, the next x, x1, is going to be x at time n minus the run. Yeah? Does that make sense? Okay, so what is the run? How do we figure out the run? Okay, well, we have something, right? We have the slope is equal to the rise divided by the run. And so we know the slope of this line. The slope is equal to g prime of x at time n is equal to the rise divided by the run. Okay? And so this leads to the run is equal to the rise divided by g prime of x at time n. Okay? And how tall is the rise? G of xn, right? So this becomes g of xn divided by g prime at xn. Okay? And so I just plug that in. And so the algorithm is this. Your next iteration's value, xn plus 1, is going to be equal to xn minus g of xn divided by g prime of xn. Let me write that a little bit clearer. And there you go. All right, so what does this require us? This requires us to figure out g prime. Okay, we got to figure out the derivative of the function for this to work.
What if the derivative at the point 0?
Well, then if the derivative at the point is 0, then it's not going to work, because your tangent line would be flat, right? It'd be parallel to the x-axis. It's not going to work. Yeah. So I mean, Newton-Raphson method is not guaranteed to work, right? So you're talking about a situation. So what if g prime of xn is equal to 0? Okay, it breaks. All right. So you're talking about a situation where it's like something like this. Okay. and you're like, oh, okay, well, this is the root we want to find. Okay, here's our root right here. And then, I don't know, somehow, you start, I don't know, somehow you end up here, okay? Well, it's not going to work, okay? If this is your x at time n, then the next iteration, whoops. Okay, it's not going to work, right? Your next tangent line is parallel to the x-axis. This is the tangent line. Okay, this will not work. I think there's an example in the homework where Newton-Raphson's method doesn't work.
If the root, at the root also, the tangent line was 0, wouldn't it also like to change to approach 0? So if you had like a really small tolerance you're looking for, you might never reach it.
So you're thinking of all these weird scenarios here, but yeah, I mean these things happen. So you're talking about like something like this, okay? And right here where my root is, this is my root. The root is also a global, like a local min or something like that. Yeah, I mean, all of these things, it's just going to converge a little bit slower, okay? And in this case, it'll take infinitely many turns to cross, but yeah, I mean, even here, it might take a bunch of iterations to cross. So, things like that happen, but, you'll still get, overall, mostly, you do your tangent line, and then you come up to here, and then you get your tangent line, and you come up to here, and yeah, you're like, it'll still get like closer and closer, and the goal of these numeric methods aren't to get exact answers, okay? We're limited by floating point arithmetic in the first place, and the goal is to just get us close to an answer, close to the real thing. The fact that you're using your computer means you've accepted a certain amount of error, okay? It's like, and you're not trying to get the pure mathematical answer, okay? So yeah, these things could happen. Okay, so let's just practically speaking. All right, so Newton-Raphson. All right, let's say our g of x is equal to x squared minus 4. All right, so, from calculus, no, not even from calculus, from algebra, we know we have a root where? Yes, thank you. X equals to 2 and x equal to negative 2, right? So that's easy. Okay, and then from calculus, we get g prime of x is equal to what? 2x. Okay, there we go. So if we were to code this up, we would probably have to write a function. G will be a function of x, and it will return g of x, which we will say is x raised square minus 4, and then we'll call this g prime, and this will be 2 times x, and then and what we will return is going to be gx and g prime. Okay, we want to return both values. If we were to code this up, right? So we get something like this, right? And then so if I called G on 5, what would it return? It would do 5 squared minus 4 and 10. And it would return a vector where we're going to get 21 and 10, right? And then so I could call G of 5 bracket 1 will give me 21, and G of 5 bracket 2 will give me 10. Okay, so I can reference the actual value and the derivative at a certain point. Okay, and so kind of our pseudocode for Newton-Raphson would look something like this, right? So we'd have Newton-Raphson. This will be a function it's going to be a function of G, an initial starting point x0, and maybe we'll have a tolerance where its default value is, I don't know, 1/1,000,000th, okay, 10 to the minus 6, right? And I'll call x old will be, we'll start off, we'll call that, we'll put x0, and then we'll set a while loop, okay, and we'll do while the absolute value of x new, maybe I have to define x new as something, okay, x new minus x old is greater than our tolerance, run the following loop, okay? And what we'll do is we'll, our latest value, x new, will become the old value, and then the new value will be our current value, x old, minus, not f, g applied to x old, and we take the first value divided by g of x old, and we take the second value, right? So this is f of x, or g of x divided by g prime of x. Okay, and then we keep running that, and then at the end of the day, we'll return x new, the latest value of x new. Does that kind of make sense for running Newton-Raphson code?
Why do you need the while loop?
Why do I need a while loop? I mean, we could just say do a whole bunch of iterations, but I think it makes sense because technically these things will run forever, right? And so we need it to stop at a certain point, and we're going to say stop when the next value you get, the next iteration is less than 1/1,000,000th, you know, less than 0.0001 different from your current value. Okay, and when that happens, we'll say, all right, that's good enough. That's good enough. Yes?
What is the tolerance? Right?
Yeah, so it's kind of a stopping criteria, right? You know, I mean, some might say like, okay, we're still getting closer to the true value of the root, right? Because if we're looking at our if we look at our previous picture here, you know, like we could zoom in and we might be like, oh, I'm getting closer, I'm getting closer, I'm getting closer. And, you know, because this is a numeric method, it might not ever get there, okay? Because every time we're like taking the derivative, like, you know, like a Zeno's paradox thing, like we're getting closer, but we never actually get there type of thing, that could happen. And so you just want to kind of say like, don't run forever, okay? There's a certain point when we'll say it's close enough, right? Okay. And so we'll say, you know, if the difference between this and the next thing is going to be, you know, less than a certain value, which we're going to call the tolerance, we'll stop, right? And obviously your tolerance needs to be bigger than your machine epsilon, which is the true limit of floating point arithmetic. Is that all right? Okay. I'm going to keep going here. All right, we've got secant method. Okay, so a disadvantage of Newton-Raphson is that you got to figure out the derivative, right? With secant method, no derivative required. Instead, you have two starting points. And so the idea here is you've got some function here, and then you'll have x0 and x1, okay? Okay, so we'll have these two starting points. So we've got g of x0 and g of x1 here, okay? And now I draw a secant line. A secant line is a line that connects these two things. So I draw a line through here and here. So not a tangent line, but a secant line. I don't know if you can see this, okay? But this is supposed to be different, all right? Okay, so two starting points, x0 and x1, and then you draw a secant line from g of x0 through g of x1 to the x-axis. Okay, so you draw through this point and through this point down to the x-axis. Okay, this becomes your next value, x2. Okay, and then the next thing, you know, again, now you come along here, and we draw a secant line through this point and this point through there, and this becomes x3. Okay, so on and so forth. And then the cycle continues. Okay, so how do we get our next value? Okay, so the next value, xn plus 1. So if we're at x1, x0, and x1, this value, so if this is, if we're going to call this xn, and this will be xn minus 1 and xn plus 1, our next value is going to be x1 minus the run, right? So we could call this the run, and this will be the rise, okay? So xn plus 1 will be xn minus the run, okay? The run is, you know, going to be the slope time the rise divided by the slope again, right? So slope is equal to rise over run. So the run is equal to rise over the slope. Okay, so here we've got xn is xn plus 1 is equal to xn minus the rise divided by the slope. So here I've got xn minus the rise is going to be g of xn, g of xn. So at time n, we're going to take this location, okay, and we're going to divide, I'm going to multiply this by 1 over the slope. Is that okay? The slope is determined by this secant line, okay? So it's the difference between kind of this run and this triangle. There's little, this is the rise and this is the run, okay? So so this becomes xn minus g of xn, okay? This part, the slope is 1 over slope, so instead of rise over run, it's going to be run over the rise. The run is going to be g of x0, no, I'm sorry, not g of x0, it's x0 minus, not, okay, we'll do basically this difference divided by that difference, okay? And so this becomes xn times xn minus 1 divided by g of xn minus g of xn minus 1. Okay? I know it's, yeah. It's this minus this. Okay. So that's the difference in the x values and the difference in the height values. Okay? And so this becomes your algorithm here. The next iteration is your current value minus this whole thing here. I guess I can get rid of the parentheses. These are unnecessary. This is okay? All right, so we've covered several root finding methods. And we can apply this to optimization, right? So here, the computer, without understanding algebra, without understanding, like, you know, trying to balance an equation or anything like that, all we're saying is just take this thing, apply a function, and, you know, get out another value, and then use that value in another step. So these are just, we're telling the computer to do these things. It's able to solve for where some function is equal to 0. Okay. And now that we can do that, we can then use this to solve for where a function has a minimum or a maximum. Okay. By applying the root finding method to the derivative of a function, we can find the critical points of a function, which should give us a local min or local max. Okay, so now that we have root finding methods, we can apply them to functions, derivatives of functions. To find the critical points, which will lead to local mins and maxes. Okay, which is what we want in optimization. All right, so you have some function f of x, and you wish to find a local min or local max. Okay, well, this requires you to find f prime of x, set that equal to g of x, and then use one of the root finding methods for g of x. Okay, and then the roots of g of x will correspond to critical points, and those should be local mins or local maxes. Is that okay? And that's one of the basic tools of numeric optimization. Okay? You might say, well, I don't know how to find the derivative. Like, you might say, well, this doesn't help because now I have to find the derivative of a function, right? So there are computational ways to get around the derivative of a function, okay? And how can we do that? You just do, if you remember the definition of a derivative, it's the limit as f of x, x plus delta divided by f of x. Wait, what? Okay, I'm sorry. It's the limit of. I can write this down. If I'm trying to speak it out loud, it confuses me, right? So and then okay, let me finish my notes here. All right. Use one of the root finding methods for g of x. Okay, the roots of g of x will correspond to local min, local max, or saddle point of f of x. Okay, mission accomplished. Okay, that's numeric optimization. Okay, we can have numeric derivatives. So this is avoiding calculus, right? So basically, so the definition of a derivative and I'm not a math teacher, so my derivative definition might be the limit as delta goes to 0 of f of x plus delta minus f of x as over delta, right? So this is kind of what we have. So on the computer, all you do is you just pick an arbitrarily small delta, like, I don't know, delta equal to 0.00, we'll say 10 to the minus 8 or something, okay? And then you just calculate f of x, and then calculate f of x plus delta, and then divide, and you do plug it in here, right? So then you do f of x plus delta minus f of x divided by delta, okay? And this will be approximate to the derivative at x, right? All we're doing is just trying to get approximate answers. So you plug that in, you get some kind of numeric approximation to a derivative. You use that to try to get what you're looking for, right? Yeah, I mean, it's messier, but okay. Is this okay conceptually here? All right, let me cover, we have a few other numeric methods for optimization. And one is the, so this is no derivatives at all. And this is called golden section search. Okay. Oh, I skipped bisection method. Sorry. Let me. All right. Just do your reading on bisection method. Okay. It's very easy. It just takes the continuous value theorem, and so if you've got some function and it crosses 0, there's a root here, and if one side is negative and one side is positive, all you do is you just cut the interval, and then you just make sure every time you cut the interval in half, you just make sure one side is negative and one side is positive. You keep the side that has the opposite sign, okay? And then you just keep cutting and you keep cutting and you keep until you close in on the space. Okay, golden section search. This is for optimization. Golden section search for optimization. Okay, the reason why it's called golden section is because it uses the golden ratio, which is about 0.618-ish, okay? And the golden ratio, the idea is that if you do 1 divided by 0.618, you're going to get 1.618. Okay. And so anyway, the way this works, okay, so you have some kind of function, and in the interval a to b, we know that there is a local minimum exists between, well, I'll do this for minimums first, okay? So we'll say a local min exists between a and b. And so here I'm going to describe it for minimization. If you want to apply it for maximizing a function, you just multiply the function by -1, find the minimum, and then that'll also be give you the maximum of the original function. Okay, so we're going to say a local minimum exists between a and b. Okay, and then you find what, I forget what letters I call these things. let me pull this up in. I call it upper and lower. Upper, lower, x1 and x2. Okay. I'm going to use the same terms that I have in the code. All right. So we'll call this the lower and the upper. So between lower and upper. These are the bounds that we use in the code. And then, okay. And then we have two intermediary bounds. Okay. We're going to have, let me just see which one is which in the code. x1 is lower plus the golden ratio and upper. Okay, so this is going to be x1 and x2. Okay, so x1 exists. This is 0.618, the golden ratio, times upper minus lower, right? I think that's what I have. So x1 is lower plus the golden ratio, and x2 is upper minus. Okay, so we're go the golden ratio up this way, and then we do the golden ratio this way. 0.618 times upper minus lower. Okay, so we've got x1 and x2, and then we evaluate the function at these two spots. Okay? And so we know that a local minimum exists between A and B, right? Or between lower and upper. Okay? We know a local min exists between lower and upper, okay? And then we evaluate the function at x1 and at x2, okay? So here we have f of x1 right here and f of x2 over here, okay? If f of x1 is greater than f of x2, as it is in this picture, okay, we know that the local minimum must then exist between the lower bound and x1, okay, and that it cannot exist between the upper bound, okay? So we'll say, we'll say one local minimum exists between A and B, okay? So we'll say one local minimum exists between A and B, or the lower bound and the upper bound, and we evaluate f of x1 and f of x2. And so if f of x1 is greater than f of x2, we know the local min cannot be between x1 and the upper bound, because there's a smaller point, x2, okay? There's a point that gives a smaller value, x2, f of x2 is smaller than f of x1. So we know that we can eliminate this section. So this can be ignored for the next iteration. We can reduce our window by that much. Okay, and here's the awesome part of the golden section search, is that if I now assign x1 is now going to become my new upper bound, x2 is going to be 0.618 between the upper bound and the lower bound, okay, because of the golden ratio. When you keep trimming things by the golden ratio, that ratio is preserved, okay? So at the next iteration, okay, so this is lower, okay, and the upper is now what was x1 in the previous iteration. Okay, and then we have our function that looks like this or something, okay? And then this value we had calculated so we can reuse the value in the last cycle, the last iteration's x2 can be kept and assigned and be called x1. Okay? So let me just kind of illustrate how this works. So just for simplicity, let's say we had 0 and 1, and our first iterations were at 0.618 and 1 minus that 0.382. Okay? And for the next iteration, we eliminate this section, right? So the next iteration goes from 0 to 0.618. And if we look, 0.382 is 0.618 times 0.618. Oops. Something happened. Okay. That's why we're using the golden ratio, because the golden ratio has this property of existing. Okay, and so now over here I would have, I need a calculator, 0.618 minus 0.382. 0.236, okay? Because if, these are approximate, but if I do 0.618 times 0.618, I get 0.382-ish, okay? And the exact golden ratio is more exact. The reason why we might want to do this is that it could be computationally expensive, like the function that we are trying to optimize. Maybe it takes the computer a while to calculate the value of the function. And so by being able to reuse values rather than have to pick two new points in the middle and calculate the value of the function for those 2 points, is that as we iterate, we only have to find one new value and calculate the function of one new value. Okay, we don't have to keep picking two values in the middle and calculating the function of those two values. So the golden section search, because of the golden ratio, allows you to just kind of keep certain things and keep going on, right? So, for example, if I had, in this iteration, eliminated this portion, okay? And so now we're at 0.236 to 0.618, okay? And we have 0.382. The distance from here to here is 0.618 times the total distance. which is 0.618 minus 0.236. I don't know. This is stupid, but so I got 0.618 minus 0.236 is 0.382. Of course it is. And then if I multiply that by 0.618, I get 0.236, and so 0.618 minus 0.236 is, of course, 0.382, right? So all of these things kind of work out, and if I go the other direction, 0.236 times 2 is 0.472. These are, the values that kind of preserve the ratio. So you don't have to keep recalculating the points. So I have it coded up here. The golden section search is applied here, and you just provided a function, a lower bound, and an upper bound. And so here we could say f is going to be a function of x, and I don't know, we'll do x squared minus 4x. Okay, so if I plot a sequence from 0 to 5 by equals 0.001, and f applied to the sequence, type equals L. Okay, so here's our function. We can see that there's a local minimum at 2. Okay, so I can just say golden f, the lower bound will be 0, the upper bound will be 5, and it searches and it tells me it has found a local minimum at 2.000002. Okay, so it's not exact. It's not exact, but this is just a computer attempting to find a local minimum numerically. All it's doing is it's starting from 0 to 5. It just chops. It says, okay, what's the golden ratio between 0 and 5? And it evaluates those 2 points, and it's going to keep, keep one side and shrink the interval, and it keeps shrinking the interval until it returns a value that's that doesn't change by the tolerance. Okay, and I could say the tolerance is 1e to the minus 10. Okay, and then it does a better job of searching. Okay, and you can give it whatever function you want to find, right? So the only requirement is that it has to be there can only be one thing, right? So maybe my function f, function of x, will be cosine of x. Okay, and so cosine of x will have, and we'll go on the interval 0 to like 6. Okay, and it says I find a minimum at 3.141593. Okay, which is great. Okay, because that's what we expect for the cosine function. There's a minimum at pi. The computer has no idea what pi is, okay? It's just plugging in values into the cosine function, and it says which value is bigger and which value is smaller, and it just compares those, and it keeps eliminating them, and it says, all right, this is the best I could do, 3.141593, okay? That is the golden section search. We're running out of time. In your homework, I've tried to describe what coordinate descent is. Okay, coordinate descent is an expansion of any of these minimization topics into a multi-dimensional setting. Okay, so let me just kind of illustrate. So imagine you've got a three-dimensional thing. Okay, you got some kind of three-dimensional graph that is my so if we draw a contour map, maybe we have something that looks like this, right? and this is your local minimum here. Okay. What coordinate descent does is you're going to minimize one coordinate at a time. So if this is x and this is y, at each iteration, instead of looking at both, you're going to just take a slice. You set, one variable to a constant. Okay, and so it's kind of, and you minimize the function for the other variable. Okay, and then you repeat, and then you do this switch variables and repeat. So basically, you start off with a function of x and y, but then maybe you set y to a constant equal to y1. So now f of x and y set to y1 boils down to just a function of x, right? So now you have a univariate function that you can minimize. Okay, and then once you minimize that, that will give you x1, and then so now you have f of x1 set to equal to x1 and y, and this boils down to just a function of y because x is now set to a constant. So now it's a univariate function that you can minimize. Okay. I think it's a worthwhile exercise to work through in your homework, and it might seem a little bit tough at first, but it's definitely doable. Okay, the golden section search function has already been written for you, so all you have to do is use that to minimize the function at each step. Okay. All right. Good luck, you guys. We'll see you guys on next week on Tuesday.